Your kernel runs, nothing crashes, and it is still wrong. A bad launch can fail in silence, a bad memory access can hide, and correct math can fail an equality test. This part makes correctness a habit. Welcome to Part 4, Correctness and Debugging. First, the errors themselves. A CUDA call can fail and tell you nothing. The program keeps running as if all is well, and you can lose hours before you notice. Let's make reading the error status a habit. You launch a kernel, nothing prints. The program exits with 0, it looks completely fine. But a launch can fail and say nothing, and the program keeps running as if all is well. The fix is a habit. After every CUDA call, read the error status and test it. First, catch CUDA errors. CUDA get last error reads the launch status. CUDA device synchronize catches what happens during the run, and CUDA check wraps the rest. Second, compute-sanitizer. It finds bad memory and it names the line that caused it. Races need a different subtool, race check, and only in shared memory. Third, verify a kernel with a floating point tolerance, not with exact equality. CUDA errors come in two kinds, and they show up at two different moments. A synchronous error, a bad launch config, is ready the moment you launch. An asynchronous error, an illegal access inside the kernel, only shows up once the kernel actually runs. Two kinds, two moments. Case A is a config error. The launch asks for a block of 2048 threads over the 1024 limit, so the launch is rejected. Right after the launch, CUDA get last error returns the invalid configuration error, shown in red. Because the launch was rejected, the kernel never runs, shown as the grayed out bar. So CUDA get last error, right after the launch, catches the bad config, and the kernel never starts. Case B is a runtime error. This time the launch is valid, so the kernel will run. The bad index inside it faults only then. Right after the launch, CUDA get last error is clean and green, because the launch itself was fine. The kernel executes. A bad, out-of-bounds index inside the kernel faults, and that only surfaces later at CUDA device synchronize, shown in red. So these are two separate runs. A config error caught at the launch check, and a runtime error caught at the sync check. The triple angle brackets launch is an expression that returns void, so you read the status right after it. The kernel is launched with the triple angle brackets, blocks, threads. Then CUDA error type equals CUDA get last error because the launch returned nothing. Then, if is not equal to CUDA success, print the error text from CUDA get error string. Reading CUDA get last error is not enough. The if is the point. An unchecked status is the same as no check at all. CUDA get last error reads and clears the current CUDA error state. Right after a launch, that state is the launch or config status, though it can also surface an earlier asynchronous error. CUDA get last error reports the launch status. To catch what happens inside the kernel, you have to wait for it. Set to CUDA device synchronize. This waits for the kernel to finish. Then, if is not equal to CUDA success, you have a runtime error and you print it. CUDA device synchronize makes the host wait for the device, then returns the runtime status. An illegal access inside the kernel shows up here, not at the launch. Time to predict. These are two separate runs, not one. In run 1, a block of 2048 is over the 1024 limit, which probe catches it and does the kernel run. In run 2, the launch is valid, but the kernel writes out of bounds. Which probe catches that? Pause the video and work it out. In run 1, the bad config is known at launch, so CUDA get-last-error catches it, and the kernel never runs. In run 2, the launch is valid, so the kernel runs. The out-of-bounds write happens inside the kernel, so CUDA device synchronize is where it would surface, and only if the hardware notices it. In the next section, we will see a run where nothing is reported at all. Writing that if after every call is tedious, so wrap it once in a macro called CUDA check. CUDA check takes a call and runs it, storing the result in CUDA error type E. If E is not equal to CUDA success, it prints the error text from CUDA get error string, plus the file and line, which come from the built-in file and line macros. Then it exits. It checks the returned CUDA error type, prints the file and line, and stops the program, so no failure goes unchecked. Now wrap every runtime call and the 2 launch probes in CUDA check. CUDA check wraps CUDA malloc, and CUDA check wraps CUDA mempy. After the launch, CUDA check wraps CUDA get-last-error for the launch error, and CUDA check wraps CUDA device synchronize for the runtime error. Now no return code is ever ignored. CUDA check turns each call's return code into a gate. The call flows in, and one of 2 things happens. On CUDA success, the program carries on. On any error, it prints the file and line and aborts. Success passes straight through. An error stops the program at the exact file and line. The classic mistake: you check CUDA malloc and then you never check anything after the launch. People check CUDA malloc and feel safe, but the launch returns nothing, so there is no return code to check. You must call CUDA get-last-error yourself, plus a later CUDA device synchronize. Skip both, and an illegal access inside the kernel goes unnoticed, until some unrelated later call fails with a confusing error, far from the real cause. Let's recap. The launch returns void, so call CUDA get-last-error right after it for the launch error and test it. A later CUDA device synchronize surfaces the runtime error from inside the kernel, and wrap every call in CUDA check, so no silent failure goes unchecked. Next, a tool that finds the bugs even a clean run hides. A kernel that runs without crashing is not the same as a correct kernel. Compute-sanitizer inspects each memory access as the kernel runs, and it points straight at the offending line. Your kernel runs, no crash, no error, so it must be right. Not necessarily. A bad write can land on still mapped memory this run and cause no visible error. Then it corrupts data or crashes on the next run. Compute-sanitizer finds these silent bugs and points at the line. Compute-sanitizer has 4 subtools, 1 for each kind of bug. Memcheck finds out of bounds and illegal memory access. This is the one we use now. Racecheck finds shared memory data races. This course does not use it. Incheck finds reads of uninitialized global memory. Synccheck finds misused barriers, like sync threads. Memcheck is the one to use now. Racecheck is the tool for shared memory races, and this course does not use it. Take vector add, but drop the if I is less than in guard. It compiles, and it often seems to run fine. The kernel vecadd computes I as block index x times block dimension x plus thread index x. Then it writes C at index I as A at index I plus B at index I. There is no guard, so I can run past n. With more threads than elements, Each out-of-range thread would attempt 3 invalid accesses. It reads it at index I, it reads B at index I, and it writes C at index I, all past the end. But the sanitizer stops each thread at its first error, the invalid read, so the report shows 1 error per out-of-range thread. Rerun the buggy kernel under compute-sanitizer with the memcheck tool. 1 red marker travels to the bad line. The marker starts at the top of the kernel. It travels down to the index line. It lands on the line. C at index I equals A at index I plus B at index I. A red box highlights that line, and the report names it, an invalid __ global read. The marker lands on that one line, a box highlights it, and the report names the invalid access. Launched with 4 blocks of 256, with n equal to 1000, the global indices 1000 through 1023 run past the end. That is 24 threads. Compiled with -lineinfo, the report names the file and line. The memcheck report reads, invalid __ global read of size 4 bytes at vecadd plus 0x70 in vecadd.cu line 4 by thread 232 in block 3. The same report then repeats for the other 23 out-of-range threads, 233 through 255. After those comes one more line. The program hit CUDA error launch failure, error 719, on the CUDA AP I call to CUDA device synchronize. That is why the summary reads 25 errors, 24 memory errors, 1 per out-of-range thread, plus that one API error. This capture is from a Tesla T4 with CUDA 12.8 and compute-sanitizer 2025.1. The offset plus 0x70 belongs to that chip. Another GPU prints a different offset. Build with nvcc-lineinfo or -G, and the report points at vecadd.cu line 4. That is the line you fix. Notice the report names thread index and block index, not the global I block 3 times 256, plus thread 232, equals 1000, the first index passed in. Leave -lineinfo off, and the report still names the kernel, the instruction offset in the thread. What it does not give is the line. It reads, invalid __ global read of size 4 bytes at vecadd plus 0x70 by thread 232 in block 3, address is out of bounds. Notice what is missing. The words in vecadd.cu line 4. So what disappears is the file and line. You still get the kernel name and the offset plus 0x70, but an offset is not a source line. You know which kernel, not where. So always build the debug run with -lineinfo so the tool can name the line. Put the guard back, rebuild, and run the sanitizer again. 0 errors. The guard is back. If I is less than n, then write C at index I as A at index I plus B at index I, that is the guard the extra threads needed. Now the error summary reads 0 errors. A clean sanitizer run, 0 errors, is the evidence a plain run cannot give you. Let's recap. A kernel that runs without crashing can still be wrong. compute-sanitizer with the memcheck tool finds bad memory, and with -lineinfo it maps it to a source line. Racecheck is the tool for shared memory races, and this course does not use it. Run the sanitizer before you trust any kernel. Next, the last correctness trap, floating point. Your GPU kernel is correct. Your CPU reference is correct, and yet an exact equality check fails. The reason is floating point. Addition is not associative, so a different order can give a slightly different answer. Your GPU result is right. Your CPU reference is right. Yet the check, assert GPU equals CPU fails. There is no bug. The GPU combined the numbers in a different order than the CPU, and floating point addition is not associative, so the low order bits differ. In exact math, a plus b then plus c equals a plus the quantity b plus c in floating point. It does not have to. Each plus rounds to the nearest value it can store. Regroup the additions, and the rounding happens at different steps, so the final bits can differ. Take the same three numbers 0.1, 0.1, and 2.7 and add them in two orders. Grouped as a plus b, then plus c, you first get 0.2, then add 2.7, and you get 2.9000001. Grouped as a plus the quantity b plus c, you first get 2.8, then add 0.1, and you get 2.8999999. The last digit differs by about 1 unit in the last place. So left equals right fails. But the absolute difference within a tolerance passes. 2.9000001 against 2.8999999. Exact equality fails, but a tolerance passes. The common bug is to verify a float result with double equals. The same numbers, regrouped, break it. Float is 0.1, b is 0.1, c is 2.7. Left is a plus b, then plus c, which is 2.9000001. Right is a plus the quantity b plus c, which is 2.8999999. The assert left equals right fails, even though the code is correct. Both lines are correct arithmetic. It is the test that is wrong, not the code. Compare with a tolerance that combines an absolute floor and a relative term, not with exact equality. Abs tall is 10 to the minus 6, and rel tall is 10 to the minus 5. Diff is the absolute difference of left and right. Mag is the larger magnitude of the two. If diff is less than or equal to abs tall plus rel tall times mag, then accept the result. Combine an absolute floor, abs tall, with a relative term, rel tall times mag. The absolute part handles values near 0, and the relative part handles large values. A pure relative tolerance collapses to 0 near 0 and would reject them. Exact equality is fine only when the same operations run in the same order. Order is not the only cause. The compiler may fuse a times b plus c into one fused multiply-add instruction. A fused multiply-add computes a times b plus c with a single rounding instead of two. The answer is usually more accurate, but it can differ in the last bits from a separate multiply, then add, so it too can break exact equality. You get bit-identical results only when the exact operation order is fixed. Same grouping, same associativity, same fused multiply-add choices. Reorder or fuse, and the low-order bits can change. So verify within a tolerance and pin the order only when you truly need bit-for-bit repeats. Let's recap. Floating point addition is not associative, so a different order can change the last bits. Verify a float kernel within a tolerance size to the data, not with exact equality. Fused multiply-add and parallel reordering also move the last bits, so bit-identical results need a fixed operation order. 1. Check every launch with CUDA get last error for the launch error and test it. 2. Synchronize for runtime errors with CUDA device synchronize, which surfaces what happens inside the kernel. 3. Wrap every call in CUDA check, so no silent failure goes unchecked. 4. Run the sanitizer with -lineinfo, and it points at the bad line. 5. Verify within a tolerance because floating point is not associative. Avoid exact equality for reordered or fused math. Next, part 5, the memory hierarchy.